So we're going to dig into our kind of rudimentary distribution here, the basis that we're going to use to explore a bunch of other distributions. And that's going to be the Bernoulli distribution. People refer to it as a distribution. I tend to call it a trial. Okay, so a Bernoulli trial. We already talked about the uniform distribution and just a little bit. We didn't really go into it that far, but we can represent that with something like random.choice from some list, right? And that'll get us a discrete uniform distribution where every outcome has equal probability. The reason why we're not going to dig that far into it in discrete distributions is we're going to cover it a little more completely in continuous distributions, the day lecture that we have on those. So let's look what's on the docket today. We're probably not going to get through all of this. Basically, we're going to start here. We're going to start with the idea of a Bernoulli trial. And we're going to take very procedural approaches for a lot of this stuff, right? We're going to write code for pretty much all of this. We're going to take something that looks like a sidestep into binary, but we're going to use binary as a basis for understanding the binomial distribution. And we're going to see that through both counting and sampling. And then finally, we'll get back to this idea of the PMF and the CDF. So throughout this, we're going to be using dictionaries. And from here on out, you want to put some time, some energy into making sure that your skills in list manipulation are, pretty decent, and also get very used to using dictionaries. We focus on dictionaries in the technical interview, and we focus on the discrete distributions in the technical interview as well. So with that, let's start talking about the idea of a Bernoulli trial. So I'm going to pull this slide up, and then I might draw a picture here, but I think this is a pretty straightforward idea. A Bernoulli trial, it's a single event. Think about a coin flip. I think that's very helpful when thinking about a Bernoulli trial. If you have a fair coin, the probability of success is 0.5. And we define success in some way, right? We can define success as getting a heads in a coin flip. In the example we have here, we can see kind of a different sort of Bernoulli trial where the idea of success would be, let's say, the probability of drawing a red ball out of a bag that has 30 red balls and 70 blue balls, right? And the probability of red there is going to be 0.3. Success for a Bernoulli trial in that instance is going to be 0.3. I think last time I talked about this in terms of pulling names out of a hat. Oh, no, I'm sorry. That was a uniform distribution because I had 3 names. But let's think about this. We'll just make this a little more concrete. Let's represent a success as being a 1 and a failure as being a 0, right? And so here are the two possibilities. If we have a single trial, right? If we have a single trial, like let's say that 1 represents heads. Oops. It's always a danger. I'm going to reach too high and move the palette or the canvas. Let's think of a coin flip where 1 is heads and 0 is tails. And in this case, we've got a probability of 0.5. We're going to reuse this letter P in general, lowercase p, to represent the probability of a single Bernoulli trial. Okay, so you might flip the coin 1 time, and there's a 0.5 probability you're going to get heads, right? Or there's a 0.5 probability you're going to get not heads. Same kind of thing. If we change the phenomenon, right? I think what we were talking about was, we've got this bag and there's 30 red balls in here, and then 70 blue. right? So there's a lot more of the blue. We can say that the probability of red here, if we define red to be the success, the probability of red is going to be 30 out of 100, right? Or 0.3. So in this case, there's a binary outcome, right? You're either going to get a red ball or you're going to get a blue ball. And we can name, if we define success to be getting a red ball, then we can see that the probability of that is 0.3. That's a very simple construct, right? A Bernoulli trial is a very simple thing. People call it a distribution sometimes. I don't like calling it a distribution because there's just this binary outcome. I think of it as a single outcome with two choices. So I'm going to have you code a function here. And I'm going to give you a little start on it where we say from random, import random. And let me show you what this function does. If we call random, let me just get that. If we call random, we're going to get a value between 0 and 1, okay? So let me call that again. Notice now it's 0.46, now it's 0.48, now it's 0.39 and 0.96, right? We can see that random will deliver us a number, a uniformly distributed number, right? This is a continuous uniform draw from random, right, between 0 and 1. That's going to be some float value, right? So that's what random does. You're going to likely want to use that in your function. You're going to code the Bernoulli function, okay? And we'll put in a probability of success. That's the parameter you're going to take. So what this should do is return either 0 or 1, okay? You could return false or true, but think about what would make this, think about 1 as a success or think about true as a success. We can kind of use them interchangeably here. So let me give you this little header. And paste that in. So you're going to write this Bernoulli function utilizing the random function that I just put in there. And you want to pass in a probability of success and either get a 1 or a 0 back, depending on your draw from random. So I'll set a timer for 4 minutes and go ahead and code that. Okay, so let's look at how to code this. We're going to call to random, okay? And I'm going to do this in a little bit of a longer hand than we need to. I can say draw gets random, and that's going to get us a number between 0 and 1. And once we have that draw, we can check to see if it's less than the probability of success. And so I can say if draw less than the probability of success, then we can return true, or we can return 1, okay? Either way is fine, and otherwise we're going to return 0. So there's a question that people almost always ask here. Is it different to say less than or less than or equal to? And what I'm going to say is that it doesn't matter. You can use less than or equal to here because when we're putting in the probability of success, we're not dealing with the extensive float. And I can demonstrate this by printing this draw, right? So let's print both the probability of success and the draw. And let me just call this with probability of success being 0.3789546. I'll call Bernoulli. Notice that this is a fairly precise thing that I put in here. My probability of success here is fairly precise, but look at the precision on the random float that's generated. It far exceeds the precision that I'm likely to put in here. I think it's rare that we're going to be doing something, quite so extreme as this. And notice where does that leave off? So 7255966. We lose our float precision right here, and we end up representing this anyway, right? So I think in this case, I'm inclined to just use less than, and with the assumption that it's never actually going to be equals to, right? I think less than is going to be fine, and we're not going to see any kind of statistical difference between those. Okay, so let me paste in this code. Feel free, if you want to change these returns from 1 to true and 0 to false, that's completely legitimate. In fact, if I haven't shown this before, let me go ahead and show this. I'm going to open IPython, and let's add true plus 5. That equals 6. Let's add false, minus 4. That's -4. So we can use true and false as if they're integers, where false is equivalent to 0 and true is equivalent to 1. That's convenience in Python. But that same convenience we can turn around here and see this as returning 1 or returning 0, or returning true or returning false. Either way is completely fine. So let's think about this Bernoulli trial a little bit further. We've got this function, and I'm just gonna, maybe I'll just screen grab this and put it off to the right. We can verify this, okay? We can verify that this function is doing what we think it's doing. And the way we might do that is we set a number of trials, and let's do 1,000 trials. And let's look at the count of trues, okay? Let's set the true count to 0 and say for whatever in range, this is the number of trials, right? And if Bernoulli, with a probability of success equal to 0.5, if that is equivalent to 1, then let's increase our true count by 1, okay? And we can do this and then print the true count over the number of trials. And maybe I'll just round this to, let's do 4 places here and see what we get. So we're getting 0.481, 0.493, 0.514, 0.517. And you know, this is a random process, so we're not hitting 0.5 exactly, but we can always increase the number of trials. And let's try that and see what happens. 0.4981, 0.5037. We're getting closer and closer to 0.5. And if I add just a couple more, you know, this is going to take a little bit longer, but we're getting 0.5 exactly once we actually average that out. So that's something to keep in mind, that you can always verify your assumptions about the function that you write. So here's that snippet of code if you want that. And as always, this is syncing up to the GitHub repository. Okay. So we're going to start approaching the binomial distribution at this point. All right. So let's first consider what the binomial distribution is asking. Let's say we have a series of trials with success or failure, right? And let's represent, again, let's represent failure as 0 and success as 1. All right, so this is a single, the outcome of a single Bernoulli trial. The binomial distribution is a series of Bernoulli trials. And what we're generally considering is the number of successes, right? The number of successes in n trials. So we can start thinking about this in terms of counting. We can recall combinations here somewhat, and we'll see where combinations fits in when we get into the PMF. So how do we count in binary? We've done a lot of counting. Let's approach counting in binary again. This will be some review, but let's think about this in, well, let's think about what binary is, right? Binary has 2 possibilities, 0 or 1. These are the 2 numbers in the system. And we can start by talking about, well, there's this thing, 1-bit binary, right? And I'm going to start using bin to talk about binary. So 1-bit binary, if we count in that, we can only count 0, 1. Okay. So let's consider instead 2-bit binary. We say 0, 0, 0, 1, 1, 0, 1, 1. So that's binary. The equivalent decimal, which I'm going to show as DEC, capital DEC for, and I'll probably say DEC for decimal. The equivalent here, 0, 0 is 0 in decimal, 0, 0, 0, 1 is 1 in decimal, 1, 0 is 2 in decimal, 1, 1 is 3 in decimal. So that's as far as we can count in 2-bit binary. Let's count in 3-bit binary. So here's 3-bit binary, and I'll put DEC over here, and we can say 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And the equivalence here is 0, 1, 2, 3, 4, 5, 6, and 7. The highest we can count in 3-bit binary in this representation is to the number 7. Apologies if I said in 2-bit binary we could count to 4. We can actually only count 0, 1, 2, 3, but there's 4 potential values that we can represent in 2-bit binary. There are 8, right? There are 8 potential values between 0 and 7 that we can represent in 3-bit binary. So how do we count this? We can count this using nested for loops, right? That's one of the ways that we do this. And that's fairly straightforward. I think we've done quite a bit of this. So here's my binary. And I'll just set this to 0, 1. And if I say for bit 1 in binary, and then let's count in 4-bit binary, where we have bit 1, bit 2, bit 3, if I can get there, and bit 4. We can, I'm just going to print this. We can print bit 1, bit 2, bit 3, bit 4. And, you know, I just want to be careful here. Bit 4 is the bit that's going to change the most, right? It's going to change twice for every time bit 3 changes. So we'll see that. Just Python Bernoulli. And notice we have 0000, 0001, 0010, 0011, and we can continue this down to 1111. There are 16 possibilities here, and we can represent decimal values between 0 and 15. Actually, I think at this point, I want to move this over to the binomial file. So I'll do that. Yeah, there we go. All right. Maybe I'll just do 4-bit binary as an empty list, and then I'll append to that list. And then I'll say for binary in 4-bit binary, let's just print each of those. So that should do the same thing. I'll just run it to make sure that there isn't something weird in there. And it looks like that's fine. Okay. So you can imagine how we might take this a step further, right? We might put another nested loop in there, and that would get us 5-bit binary. Or we would put, you know, a bunch of nested loops and do something like 16-bit or 32-bit or 64-bit binary. That's a lot of nested loops, and that's probably not what we want to do. So we're going to work on, very shortly, we're going to work on an algorithm that I think is pretty cool. I think it's the kind of thing that that it's, you know, it's a good algorithm to know, called the deck to bin algorithm. But before we do that, let's think about the process of converting binary to decimal. And I'm going to have, I'm going to use an 8-bit binary word. That's what we call that. We call these binary words, which may be a little bit strange. We don't call them binary numbers usually, but I'll just point this out. If I say binary word, I mean binary number. You know, it's really the same thing for our usage here. Okay, so let's start with this number, this binary word 101101110. And let's think about the place values here. This is, I'll do this in red. This is the ones place. This rightmost bit is the ones place. This is the 2's place. This is the 4's place. This is the 8's, the 16's, the 32's, the 64's, and the 128's. So when we think about this, if we break this down, we can think of this 1 or 0 as being like an on-off switch for the place value, right? And one of the first things we can see is that we don't contribute a 1 here, right? So this is 1 times 0, which should tell you offhand that this is an even number, right? We're not putting a 1 in here. This is 1 plus 0. We have 1, 2, right? 1 times 2 plus 4 times 1, or 1 times 4. Probably be consistent here. 1 times 4 plus 0 times 8 plus 1 times 16 plus 1 times 32 plus 0 times 64 plus 1 times 128. And if we look at this, well, this is just 128 plus 32 plus 16 plus 4 plus 2. And if we add all that up, that's what, 160, 176, 182. I think that's 182. And thus we can see that a representation that this binary word can have in decimal, 10110110, for us, we can say that that is equivalent to the number 182 in decimal, okay? So you can break this down into an algorithm, right? We could write a function that is binary to decimal, where we feed it a binary word and we get out a decimal value. We could do that. And you might want to think about doing that just for fun. But what we're going to do instead is work on a different algorithm that is the decimal to binary algorithm. Otherwise, the way that you'll hear people refer to this is as dec to bin. And let's talk about what this algorithm is. Let's think about how to do this. And I like this algorithm because it's simple and it's not obvious just by looking at it what it's doing. So here it is. It says given a decimal number. I don't know why decimal. Let's think about this instead as given a number or a base 10 number. Decimals here seems to imply a float, and I think it would be nicer to say just base 10. Given a base 10 number, and we're probably going to just use integers here, although you could code this differently for float values, but that would be much more involved. So let's say given a base 10 integer, you're going to take the modulus of that number by 2 and set aside the result. Now, what are the two possibilities for taking, what are the two possible results for taking modulus by 2? What are those? Yeah, 0 or 1, right? So you can already see in this, there's a conversion to binary. And then we're going to floor divide the number by 2, right? So we divide it and throw away throw away anything that's a decimal value. And we keep doing those things. We keep doing this until the original number is reduced to 0. And then what we get out of that is a, kind of this list of binary. We reverse that list, and that's actually the binary representation, or a binary representation of that number in decimal. So let's convert. This is a little bit of pen and paper stuff, but I think this is nice. So let's do conversion of 1, 0, 1, 0, 1, 1. It's relatively short. Which is the conversion of 43. So we're actually going to start with 43 and convert to 1, 0, 1, 0, 1, 1. So if we're following this algorithm, and I should have just left that open so that we can follow along with it. I'll put this in the bottom right. The first thing we're going to do with this 43 is do 43 mod 2. Okay, so 43 mod 2 is going to give us 1, right? We have a remainder of 1 there. And then we floor divide by 2, which is going to give us 21, right? It would be 21.5. We throw away that 0.5. So 21 mod 2 is going to be 1. And then 21 floor divide 2 is going to give us 10. 10 mod 2 is going to be 5. Oh, sorry. 10 mod 2 is going to be 0. And then floor divide by 2 is going to be 5, right? 5 mod 2 has a remainder of 1. And then 5 floor divide by 2 is going to be 2. 2 mod 2 is going to be 0. 2 floor divide 2 is going to get us 1. 1 mod 2 is going to get us 1. And then 1 floor divided by 2 is going to be 0, of course. And at that point, we would just keep getting zeros, right, forever. So if we take this number and we start at the bottom, right, we can rewrite this. I'll just rewrite it over here. 1, 0, 1, 0, 1, 1. And we can see that that is indeed the conversion from 43, decimal 43, into binary of 101011. The way integers are stored is a little more complex than that, honestly, but that's fine. This is kind of the rudimentary idea, and we're going to use this. We're going to use this algorithm in coding the dec-to-bin function. So I pointed out here that we could keep putting zeros at the front of this, right? 101011, 101011 is the same representation as 0, 0, 101, 011, right? Whereas this first one is 1, 2, 3, 4, 5, 6-bit binary, right? This is 6-bit binary. This lower one is 8-bit binary. And all we've done is we've padded zeros on the left here. So the function you're going to write is going to be called dec-to-bin. And it's going to have two defined parameters. One is going to be a decimal value, right? Like the number 43 or 129 or something like that. And the second thing is going to be the number of bits, okay? So the number of bits, if you put in 8 bits, right? Number of bits is 8, then, and you put in the decimal value 0, right? So this would be, dec-to-bin of 0, 8. This should give you 1, 2, 3, 4, 5, 6, 7, 8, right? Similarly, if it's dec-to-bin of 1, 8, this should be all zeros and then a 1 here, okay? If this is 16, well, then you need to pad 8 more zeros in front of this. So let me grab that breakout. And if you've done computer science courses, this is like a classic computer science problem. But we're going to turn this into something related to binomial in just a little bit. So this is the thing you're going to code. Let me put 6 minutes. In fact, let me put 7 minutes on this timer. Do your best with this. Dec to bin takes the decimal value as the first parameter, the number of bits defaulted to 8 as the second parameter, and you should follow this algorithm and return the binary representation of that decimal value. So go for it. Okay, so I'm not seeing. Okay, I'm seeing a couple solutions come in. If you're still working on this and want 2 more minutes on it, I know this isn't the easiest thing. If you want that, give me a thumbs up. Otherwise, I can go ahead and start coding this out. Yeah? Okay, great. I'll give y'all. Let's do 3 more minutes because I think this is fun. I think this is a fun algorithm, and I'd like to see a few more of you get to there. So. Okay, let's code through this. Oops. All right, so the name of this is, oh, you know what? Let me go ahead and pull up that, just have that algorithm still sitting up here. I think it's helpful to have up over there. And we're gonna say, define this as dec to bin. Maybe I'll make this a little bigger. Def dec to bin. And we're giving this a decimal number that I'm going to call dec, and a number of bits, which is going to be how long of a binary word we return. So I'm going to do this as a simple collector. I'm going to make a binary list, and I'm going to make a copy of dec. Okay, so given that dec is an integer, we don't actually have to do anything like this. We can just say x is the same as dec. That way we're not modifying the parameter. So I'm going to say for whatever in range, and the cool thing about this algorithm is that we only need to perform this operation n bits times. And there's something I'm going to show you immediately after that I think is kind of cool about this as well, and leads into some ideas in discrete math. So the bit that we're going to get out of this is going to be this take the modulus by 2, so x mod 2. We're going to set that bit aside into the bin list, right? We're going to append the bit, and then we're going to contract x. We're going to floor divide it by 2, so x floor divided by 2. And when we return this, there's a couple different syntaxes you can use here. It is totally okay to say this, list of reversed of bin list, right? But the more Pythonic way to do this is with list slicing, which would look like this. So bin list, and this just represents the whole list, and we want to traverse it in reverse. So we're going to say : -1, and that'll get us the reverse list. So let's call this function dec to bin, and let's pass in 43 and see what happens. Bit list is not defined. Oh, well, that makes sense. Just change these to bit list instead. Okay, 001, 01, 011 is what we're seeing. And, oh, I guess I erased that. Let me just double check that that is correct. 101011 is what we should see. And that is what we're seeing, 101011. But we said 8 bits, right? So here's a thing that maybe has occurred to you. What if we are asking for the conversion of the number 43, but we're only provided 4 bits, right? What do we get out of that? 1011. And 1011 is 1 plus 2 plus 8, right? So that's actually 11. So you can kind of see in, there's some kind of, in discrete math, there's some kind of equivalence between the number 43 and 11 in a binary system. But that's a whole different wormhole that we could jump down that we're not going to. The takeaway here is that we could put in, say, 64, which is a common length of storage in computers. And notice in this representation that we've defined, we've got this massive list, but the only meaningful values are here, 101, 011. I think we're probably going to stick to smaller lengths of list. So now that we have this function, we can do some stuff with it. And this is going to bring us back around to what I'm going to call a binomial process, the binomial distribution. And just as a reminder, I'll say this again, we've got a Bernoulli trial, right? A single Bernoulli trial would be either 0 or 1. And a series of Bernoulli trials would be, right, this experiment n times, right? This would be 4 times. And we're either going to have a 0 or 1 in each of these places. If we want to be exhaustive about the possibilities of number of successes, well, we can count, right? We can count in binary. We can say 0, 0, 0, 0, 1, 1, 0, and so on for 4-bit binary. We could do that with nested for loops. But now that we have this dec to bin function, we can make an arbitrary number of trials. And that's kind of cool. So why don't we do that? I'm going to do this by collecting, starting off by collecting values into a dictionary. Okay, so I'm going to write this function called getBinary. Sorry, am I going to write a function called getBinary? Yeah, I think I will. Okay, so getBinary. And what this is going to do is it's going to populate a dictionary where the keys are decimal values and the values are the binary lists that represent those decimal values. So let's call this n bits. And I'm going to make a dictionary to hold this, right? And this is how I like declaring dictionaries. You're welcome to declare dictionaries like this. I really do prefer this. It tells people it's a dictionary. And I'm going to say for each decimal value in range. And here's kind of a thing. I could put a low to a high, right? I could say from 23 up until 476. But instead, I'm going to be exhaustive, going from every decimal value from 0 up until the highest value that I can store. So what is the highest value that I can store for 8 bits, right? Where every one of those bits would be 1, right? Where it's 1, 1, 1, 1, 1, 1, 1, 1. Somebody posted, yeah, both those answers posted are correct. We can store 256 different values, but the highest value that we can store is 255, which is 2 to the 8th power minus 1. So that's kind of cool. So a convenience here is we can just say 2 to the n bits. And this is going to go everywhere from cover everything from 0 up to 255, right? Because range is not inclusive of the rightmost value. So we can just do that. And I'm going to say, well, bins, this bins dictionary sub dec, that's the key. The decimal value is the key. We can just call dec to bin on that dec value with the number of bits. And we can return that bins dictionary. When we traverse this, I'm going to say for decimal binary in, actually, this is don't make this mistake where you just say bin. It should be bin underscore. Bin is actually a reserved word. So dec, comma bin in get binary of, let's say, n bits gets 8. And when I call that, I need to also use the .items method to unpack those dictionary items. I can print the decimal value in relation to the binary value. So let's see what that gets us. We can see the relationship here, right? 255 is all ones in 8 bits. And we can just see that we're counting from 0, which is all zeros, up to 255. Now, what happens if we put in n bits is 64? Let's find out. It's going to take a while. And that's because we're, performing this operation over and over again. If I really wanted to see this in this case, probably what I would do is cover this in real time and do something like this, where maybe I would put this in the for loop and this is two function calls. Maybe it would be a little bit better to do something like this. There's a little bit less overhead if I do that. And let's see. This way we can actually watch it count if we want. It kind of overflows a little bit. So in the representation. So maybe I'll change this to 32 and it'll be a little nicer. But if you ever want to watch binary be counted, it still overflows a little bit, but, you know, we can, you know, do that if we want. I'll change that back to 8. And I'm going to comment out that line, but I'll leave it in there because I think it's kind of nice. So let me grab all of this and throw it in the Slack. And let's revisit this idea of why binary, right? We can think of a binary word as being a series of Bernoulli trials. There's a direct way that we can think about that, and which is kind of cool. It's like, okay, if we're flipping a coin, tails, heads, heads, tails, heads, tails, 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 right? That's 8-bit binary. That actually has a decimal representation. Although we don't really care about the decimal representation when we get down to it in a binomial distribution, all we really care about is the count of successes. But now we have a scheme where we can change the number of trials very easily without having to use nested loops to analyze this, to build our subset A over the sample space S, right? We don't have to build a nested loop structure anymore to do that. So let's think about 4-bit binary really quick and relate this to binomial, and then we'll take a break. If we're thinking 4-bit binary, 0000, 0001, 0010, 0011, 0100, 0101, 0110, 0111, 1000, 1001, sorry, 1001, 1010, 1011. If you want to really seem like the weirdest person in the room, just count in binary, right? People will really wonder about you. So this is all the values for 4-bit binary, right? And if we're talking about the number of successes, we can make a simple histogram here where we say, well, there's 0 successes, or there's 1 success, or 2 successes, or 3, or 4 successes. The maximum number of successes is 4. And we can populate this histogram by simply counting the occurrences of these. So there's one instance where there's 0 successes. There's 1 instance where there's 4 successes. And keep in mind, this is with a probability per trial of 0.5, right? We keep a consistent probability across all trials, probability of 0.5. Now let's count how many times 1 occurs. So 1, 2, 3, 4 times. That's it. 1, 2, 3, 4. Let's count the number of times 3 occurs. It's going to be 1, 2, 3, 4, and that's it. 1, 2, 3, 4. Let's count the number of times 2 occurs. 1, 2, 3, 4, 5, 6. That's the shape of a binomial distribution with a probability of 0.5. So that's kind of nice. We can see this. We can see this from the root of a phenomenon, right? We can see this from a place of, well, we're flipping coins or we're counting in binary, right? We can see an underlying phenomenon here. Now, it is a little bit tedious by hand, of course, to do this, especially if we have like 8-bit binary. We're probably not going to do that. But we can use, we can construct the binomial distribution using a dictionary in the analysis of the process that we just created. So let's take a 5-minute break, and I'll see y'all back here, and we'll do that. Okay. All right, see y'all back here in a few minutes. All right, let's get back to it. So what we're going to do is we're going to construct a binomial distribution for n trials. And there's going to be a fixed probability here of 0.5. So when we're thinking about the binomial distribution, and this is important to remember, when we're thinking about the binomial distribution, there are two parameters to this distribution. And I'm using that term parameter in a statistical context, not in the context of the parameter to a function. However, it's kind of interchangeable in this case, except in this case we also have to keep a fixed probability p. So, given the scheme that we've come up with, we'll come up with another scheme where we can vary the value of p. So the two parameters are n, which is the number of trials, right? If we have 4 trials, we represent that with 4-bit binary. That's what we've been doing. And p, which is the probability, right? And we're fixed here at 0.5. We have to use 0.5 in this scheme. So let's look at how to do this. I've said this before, but I'll just say it again. We expect you to know how to use dictionaries pretty well for the technical interview. And there's some different reasons for that. One of the primary reasons is it's a somewhat complex data type within base Python. And we can use it to do kind of cool things like show a relation between decimal values and their binary representations. Or in this case, what we're going to do is show the number of successes in relation to a count of successes and then a probability of that number of successes in n trials. So I'm going to define a function here called binomial distribution, and we'll default the number of trials to 8. And we're going to make a dictionary here as a collector. So the way that we're going to build this is we're going to first get a dictionary of binary values from this previous function, get binary. So we'll start off with that. And this will be binary dict, and we're calling get binary on n trials. So if we were to set this at 64, we could actually still do this. It would just take, a long time, longer than we want to take right now. Okay, so I'm going to say, notice that we have decimal values related to binary representations. We don't actually need the decimal value here. So I'm going to say, I'll say for underscore, that means we're going to throw it away. It's disposable. For underscore, comma bit in bin dict.items, the sum of the bits. Actually, this is a binary list, isn't it? Let's call it that. The sum of the bits in that binary list is going to be the sum of bin list. That's really straightforward. We're just summing the ones, right? We're summing the successes. And then we can say if the sum of the bits does not already exist in the binomial dictionary, then we can append it in there. Or sorry, we can initialize it in there. And we're building counts first. So I'm just going to initialize this to 0. And then this is the syntax I like for doing this. I'm just going to increment it by 1. So that's going to get us the start of something. Okay. So we'll return the binomial dictionary, and I will first call this binomial distribution of n trials, and let's set the number of trials to 12, right? So the potential range here, the range of successes is from 0 to 12. The most successes we can have is 12, the least is 0. That would be all zeros versus all ones. And I can traverse this. I can say for kv in d.items, let's just print an f string of the, well, we could call this k and count. Oh, that's not a great name, actually. I'll just do that. And let's see what we get out of this. And here is a binomial counts dictionary, okay, with a probability of 0.5. Offhand, how would we get the probabilities of having 5 successes in 12 trials? How would we figure that out? How do we represent the probability of 5 successes in 12 trials given what we're seeing in this dictionary? If you want to provide like a little code snippet, however we want to think about that. So maybe this isn't entirely obvious, but what you can do, and I think this is, part of, when we get back to that cardinality of A over cardinality of S idea, we can say D sub 5, which is, when we're looking at this, that's this value, 792, over the sum of D dot values, which is all of the, all of these values. We could also say, 2 to the 12 or something like that. So let's see what that is. Looks like that's, roughly 0.19. And the, just to be clear, the question we've answered there is, what is the probability of, say, 5 heads in 12 coin flips of a fair coin, right? In this case, n is 12, p is 0.5, and this will actually get us that probability. We can be a little bit more complete about this if we want to see all the probabilities, and that's going to be fairly easy to do. So we've got the counts that we show up here, through that for loop. If we want the probabilities, we can simply say for each value of k, let's round down the the count divided by the sum of d dot values. And let's not round down, but let's round that to 5 places. Is that? Yep, that should do it. And now we should be able to see the probabilities for this distribution instead. There's some things to notice in here, some important things. Oops. And these are all aspects of the binomial distribution. We've got, for a probability of 0.5, we have symmetry, right? 11 and 1 have the same probabilities, and we have some expected value here. This expected value is 0.5 times the number of trials, right? This expected value 6, and the expected probability of 6. The expected value, the thing that we would expect to see on average, is 6. And that, of course, has the highest probability. Okay. So let me give you this code, because I think this is going to be really helpful for the next breakout, or maybe necessary for the next breakout, really. I'm going to have you solve this problem. You flip a coin 12 times. N, right, that's the number of Bernoulli trials. If we think about that in terms of our function, that is the number of trials, right? N trials. K is the number of successes for which we want the probability. P is the probability of success in any given trial. What is the probability that you get 9 heads in 12 flips? So you're going to use the code that we have to answer that question. And give the values of N, K, and P. What is the probability of getting 4 or less heads in 12 flips, right? So this harkens back to the CDF, the cumulative density function. So again, what are the values for N, K, and P? So I'm going to put 4 minutes on a timer. And yeah, do your best to answer that with the code snippets that I gave you. Okay, so I'm going to go ahead and start solving this. Oh, probably need that. Grab that again. All right, so you flip a coin 12 times. Well, that's an n of 12, right? That's 12 trials. So let's just call it that. N is 12. N is 12. And what is our k? K is the number of successes for which we want the probability. What is the probability you get 9 heads in 12 flips? Well, k is 9. And then p, of course, is 0.5 because we are flipping a fair coin. All right. So what is the probability that you get 9 heads in 12 flips? The way that we can answer this, we can call out to this function. And this is going to be a little cumbersome, but we can definitely do this. So we call out to this. We pass in n trials of 12. What we're going to get from this is a dictionary, right? And there's going to be a key in that dictionary of 9. That's going to get us the count of the count of occurrences of 9 successes across 12 trials. Now, here's kind of a weird thing. We can call this again. This is like I said, this is a cumbersome syntax, but we can take the sum of these values like so, and this should get us that probability. So let's see what that is. Looks like that's 0.0537 roughly. It's probably a little nicer if we just get this dictionary in the first place and use it as it is. So I'll go ahead and adapt this code because we already have that dictionary, and we don't really need to call this multiple times. So I'll say d.values, and I'll say d sub 9, and we should get the same result. And we do. Okay, so that's the first question. Now, the second question is maybe not as obvious. And I'm going to try to make this obvious. What is the probability of getting 4 or less heads in 12 flips? 4 or less, right? Well, what does that include? That includes 4, 3, 2, 1, and 0. So what we can do is just sum each of those occurrences. So I'm going to grab this, and I'm going to do this in the long way where I say d sub 0. Let me do that and add to this d sub 1 plus d sub 2 plus d sub 3 plus d sub 4. And you're probably already thinking there's a better way to do this. There definitely is. But I want to show you that this is what we're doing in the cumulative density function. We are summing from 0 up until some value. So if I print this, we should see that probability, or we get a syntax error that is probably a little tricky to track down, actually. Open, close. Oh gosh, that's gonna be really hard to find. Okay, let's just trust that this would work. I don't want to track down that specific. That's why we don't write that. Let me say that. Okay. Instead, let's just make a simple accumulator and accumulate these values. And that'll be easy to do. We can just say, some accumulator is going to be incremented by, some value in D. And we can say let's call this K. For K in range, and we can go from 0 to 4 and increment an accumulator in that process. So we'll start the accumulator at 0, and now we should be able to just print the accumulator and have the right answer. So it looks like that is 0.1938. And if we look at earlier the output of this dictionary that we saw earlier, we can kind of verify that, right? So that's 0.00024 plus 0.00293 plus 0.01611 plus 0.05371. All of that looks like it could add up to roughly 7, right? And then we're adding that to 0.12085. So, it's always good to go back and verify that that what you think is happening is actually happening. Okay, so I'll go ahead and comment that out. Why don't I snag all of this and go ahead and throw it in the Slack. Okay. So we're going to take a different lens here. That was our counting approach, right? If you remember what we were talking about yesterday and the day before with these general analytic approach ideas, that was the counting approach. And we can move to a different approach. And binomial is nice for this because we can have very understandable versions of these events. We can take a sampling approach to the binomial distribution. So why don't we first construct the binomial distribution using the choice function from random. So I'm going to import that. And the first thing I'm going to do is I'm going to get a single bit. Okay, I'm going to get a 0 or a 1. And that's easy to do, right? We kind of know how to do this already. Call this get bit. It doesn't take any parameter, right? We're just randomly returning a 0 or a 1. So I'm going to return the choice between 0 or 1. And now I'm going to generate n bits. So generate n bits, and I'll default that to 8. And this can be a simple like collector accumulator where we have the list collecting bits that are collecting 8 bits, right? So for whatever in range n, which by default is going to be 8, we can say list.append get bit, and we can return the list. So this is only going to get us one binary word of length 8, right? If we call it with its default value. But let's just see. Make sure that it is doing what we think it's doing. And there we have it. We have a length 8 binary word. If I run this again, it's a different word. It's a different word. And we can keep doing this, and that's great. We have a binomial process, but it's not built on counting this time. It's built on sampling. And we can use this in a very different way, not even that different of a way from the counting approach that we took. And this is going to look back at when we verified the operation of our Bernoulli trial, right? So I'm going to do that in a second. But first, I'm going to rewrite this just to show you. You don't have to know comprehensions for the technical interview, but some of you will want to use comprehensions because they're fun and they're very expressive and they're fairly compact. So I'm going to just rewrite this as a comprehension. I'm going to get a bit for every number, for every item in the range from 0 to n. And then I can just wrap that in brackets. And that's a comprehension. That one line of code that we see there is doing everything that this is doing. And it's a little more efficient. But again, you don't need to use comprehensions until you get into the DSI. Okay, so I'm going to have you write a function that looks a lot like the prior functions that I've been writing. This says 4 minutes. I'm going to give you more than 4 minutes. You're going to write a function called binary sampling dictionary. Oh, you know what you're going to need? You're going to need these. So let me make sure that you have those first. Okay. So you're going to write a function called binary sampling dictionary. And that function is going to take 2 parameters. The number of bits, right, which is the length of the randomly generated binary word, and the number of samples, the number of times that you call out to that function that I just pasted in, which is called generate n bits. Num samples is the number of times that you call generate n bits, okay? And you're going to return a dictionary where the keys represent the number of successes and the values associated with those keys represent the count of that number of successes occurring, okay? So, 0, you get all zeros maybe 35 times. You get 1 63 times, and all the way up until number of bits. And just as a reminder, this is an example here, 00101101. There are 4 ones in there, so there are 4 successes. Okay, so let's do 6 minutes on this. And you're probably going to want to reference prior code and borrow ideas from that, unless you know how to code this offhand. So yeah, go for it, and then we'll go through a solution. Okay, let me know if you want a couple more minutes on this with a thumbs up. Otherwise, I will start coding it. Okay, I'm going to throw 2 more minutes in here. Okay, I'm gonna start coding this. Don't be, don't be hard on yourself if you didn't get to a solution on this. This is one of those kinds of problems that you need to solve multiple times. Okay, and this type of problem is really key in the technical interview. This is sort of the crux of the challenge, the crux of the type of challenge that we give you. So what I'm going to encourage you to do, I'm going to go ahead and write this out. I'm going to encourage you to, study the code that I write here and be able to reproduce it. So, we took this counting approach. You want to be able to reproduce a counting approach in terms of dictionary analysis. You want to be able to reproduce a sampling approach in terms of dictionary analysis. And you're going to want to, when we get to it, be able to take some kind of closed formula and express that through a dictionary as well for some range of input values. So we're calling this binary sampling dictionary, and this takes 2 parameters, num bits, which we're going to default to 8, and number of samples, which we're going to default to 1000. So the first thing we always do here is we create a dictionary to collect values. If we are considering a sampling approach for something like this, we're likely going to be counting the occurrences of some event, right? And we're going to see that. But this is going to be a fairly regular thing when we take a sampling approach, right? For whatever in range number of samples, right? We've got number of samples up here, and we have some kind of throwaway iterator right here because we don't actually care about the value of the iteration. We just want to do this num samples times. So the first thing I'm going to get is the binary, which is going to be generating n bits of length num bits, right? And from here, we want to get the kind of the observed number of successes. So let's call this num successes. That's going to be the sum in the binary, right? we can think about that as the sum of ones. We're not going to have a 2 in there. It's just the sum of ones in the binary. And if that number of successes is not already in the dictionary. So this is an aspect of this, a potential aspect of this sampling approach. If we don't already see it in there, we have to initialize it. And that's going to be d sub num successes. And the way I do this, again, I initialize it to 0, and then I say plus equals 1. In this case, I'll just show you an example of doing it the other way, the maybe more common way to do this, where we set this to 1 if it's not in the dictionary. Otherwise, we will increment it by 1. Those are equivalent statements. It doesn't matter which one you use. And there's also other ways to do that as well. And then I can just return this dictionary. So what does this look like? Well, let's find out. We're dealing with 8 bits and how many samples? 1,000 samples. So I'll get a dictionary out of this, and I'll say for k, and this is a count in d.items. Let's print the k and the count. And one of the first things that you're going to see here is, well, I'll just run it. Oh, you're going to see a syntax error because I didn't close my print statement. Okay. So something a little bit annoying here in a sampling process, we don't know that we're going to get 0 successes on the first entry into the dictionary, right? So we actually want to sort this. I'm going to do sorted of d.items in this for loop so that we have something a little nicer to look at. And we can see these counts. This is not symmetrical, but we wouldn't expect it to be because this is random, right? We're using a random approach here. And as a result, well, what are we going to do? One really amazing thing about sampling, let's just change this to 64, okay? Or let's change it to 864. Why not? I didn't mean to do that, but let's do that. Now, if you think about that in terms of a counting approach, that's going to be a small nightmare. But here, we actually can get an immediate estimation. Now, what we're limited by here is the number of samples, right? This is just 1,000 samples, so how close are we actually getting to appropriate counts? Well, we can get a read on the distribution in this case. But, let's go ahead and back that up to 8 and look at this one more time. And we can see these counts. Now, if we think about this, every time I run this is going to be different, right? And we can clearly see that. We can clearly see that every one of these is going to be a different call. Now, if we wanted to settle on some kind of theoretical counts, what we might do, or if we want to approach the theoretical counts that we would see here, what we might do is run this whole thing over and over again and take the average across all the resulting dictionaries. Like maybe we would do this 1,000 times, right? And then we're going to be converging on an actual number of counts. And we already know how to get the probabilities out of this. That's where we'll start off next time. But in the meantime, let me just do this. I can sample more, right? I can do more than 1,000 samples. And let's do 1,000,000 samples and see about that. So it's going to take a little bit of time, right? 1,000,000 samples of 8 bits, but it doesn't take that long when you get down to it. That was maybe 10 seconds, probably not even that much. And notice the more samples we take, the less relative distance there is between these values that should have symmetric counts in the theoretical distribution, right? And when I say relative distance, it's sort of like a distance ratio, not the actual distance in terms of how many, is it 10 distant or is it 15 distant? It's more like, what is that distance relative to the overall distance that we see between these values? So what you might take away from that is the more samples we take, the better estimation of the theoretical distribution we get. And that's a theme, right? Like we've brought that up before. That's and we're going to bring that up more and more as we go forward. And you're going to see that throughout data science. You're going to see that the more data you have, the better you can estimate a function. For example, the better you can estimate the actual function that represents a phenomenon that you're observing in nature. So let's stop there. And again, what I'm going to recommend is that you study this. Study this specific snippet of code. And we're going to use this in the next class pretty much immediately. The next slide on this is a breakout where we analyze these results, and there's kind of a conceptual question there. And then we'll extend this function in a couple different ways that I think will be pretty interesting. So I'll go ahead and stop recording. And